Welcome back to Mechanics of Materials. Today we're going to look at section 6.9 in the book on stress concentrations. This, as you see, is very similar to what we've done before. We're just going to look at the geometric properties in a change of cross-section of a component. So it only depends on geometry. But now the loading condition we have, of course, is bending. And just like before, they provide us with some graphs of those stress concentration factors K. And all we need to know is the geometry, which they give us in the picture. So they tell us what those are, what those parameters are. Yeah, too much stuff in the way. There we go. They tell us what those parameters are and then how to use them on the chart. All right. So let's look it up. A couple reminders of how we do this. So if we just take our bending stress, oops, sorry, let me get back up. Remember, bending stress max is just going to be equal to MC over I. But now we're going to put a K in front of it. So if we had a cross-section, it looked kind of like this. Now we always reference everything to the smaller cross-section, right? So if this is going to be this is H. All right, that's H. This is W back here, and this is the radius here. And of course, there's some thickness to this T, right? So this comes up here. So let's do an example. It's as easy as this. If we had, say, an H equal to 80 millimeters, and W is equal to 120 millimeters, and R is equal to 16 millimeters, and T is equal to where'd T go? 20 millimeters. And we're going to put a moment on here, and the moment is equal to 5 kilonewton meters. Remember, I told you it's always force times distance for a moment. So the book, the curve says the first thing we need is R over H. R over H. Well, R over H is 16 over 80, and that's equal to 0.2. Then we need W over H. So remember, everything is in reference to the smaller cross-section. W over H is 120 over 80, and that's equal to 1.5. Okay, so now what do we do with that? Well, we go to our curve. Here's our curve. And we would come up we find R over H of 0.2. Here it is. So we come up 0.2. And then we're looking for W over H of 1.5. So it's right here. And there's 0.2, right there. And then we read across, and that's 1.45. So K, from the table, from the graph, right? K is equal to 1.45. All right. So now we need to find the moment of inertia. Well, this is a rectangle. So the moment of inertia of a rectangle, right, is equal to 1/12 BH cubed. Now, you could say plus AD squared, but in this case, we don't have to move it. So D goes to 0. Let's put the numbers in. 1/12, the base. What's the base? The base is the thickness. The thickness is 20 millimeters. And the height is 80 millimeters. And that's going to be cubed. Now, if we want to put that in terms of meters, right, because our moment is in kilonewton meters. So if we want to put this in terms of meters, that's 1/12.02 meters times 0.08 meters cubed. And that's going to equal, let's see, that is going to equal 0.02, enter, 0.08 to the third times 12 divide. I get 8.5333 times 10 to the minus 7th. And that's meters to the fourth. Now we're going to calculate stress. So our maximum stress is K, which is 1.45, times M, which is 5,000, right, Newton meters, times C. Well, here's where our centroid is. So C is going to be 1/2 H. Right, that's the distance to the outer fiber from that bending. So C is going to be equal to 0.08 over 2, right? And then we divide that whole thing by I, which is 8.5333 times 10 to the minus 7th. And that's in meters to the fourth. This is in meters. This is non-dimensional. That's Newton meters. So we're going to end up with newtons per meter squared, which we should. That's the correct units. And so we're going to multiply that through. Let's see what that looks like. Let's invert that thing. 1.45 times 5,000 times 0.04 times. I get, see that, 339, 843, 7. Okay, so that looks like that's K, that's M, and we're going to round up. So it's 340 megapascals. Remember, a Pascal is, of course, just a Newton per meter squared. And mega here is 1 times 10 to the 6th. Anyway, that's our answer, 340 megapascals. So again, just to review, for stress concentrations, you always reference the smaller dimension, but look at the picture. The picture will tell you what everything is. Here's our basic equation. Maximum stress is just K, the stress concentration factor. Times our average stress, MC over I, or well, our maximum stress, really, right? MC over I. Outer fiber stress. And that's all there is to it. That's all there is to it. All right. Thank you.